Very good morning to one and all, and I welcome you in the next lecture of heat transfer. Whether my voice is audible and can you see my presentation? So here I suggest you please rotate your screen for good visualization of this particular word file, and uh, adjust screen as per your requirement by using the zoom feature. Okay, it is okay with everyone whether my voice is audible. Please comment in the chat box.
Yes, sir, it's visible.
Yes, awesome. Great, great. So, in the last lecture, we have discussed about the convection, that is the second mode of heat transfer. Okay, convection heat transfer. So, in convection, the fluid particles themselves moves and carry the heat from one region to another region, or from or from higher temperature region to the lower temperature region. Now, to govern this convection heat transfer, we discuss the Newton's law of cooling, which will govern the convection heat transfer, which will govern the convection heat transfer. And this law stated that a rate of convective heat transfer per unit area, rate of convective heat transfer per unit area is directly proportional to, the difference between surface temperature and fluid temperature, is directly proportional to surface temperature and fluid temperature. Now here we are considering, to understand this particular law, we have considered this particular figure, okay, in which this is the plate which is exposed for the convection heat transfer, okay, and which is maintained at a temperature of T suffix S, which is a surface temperature, okay, and fluid is flowing over that particular plate, okay, fluid is flowing over that particular plate. Now whose temperature is T suffix F, okay, whose temperature is T suffix F, and T suffix F is less than T suffix S, okay, T suffix F is less than T suffix S. So according to Newton's cooling law, the heat transfer from plate to the fluid which is flowing over that plate is stated as, mathematically we can say that heat transfer rate per unit area, that is Q by A, is directly proportional to temperature difference between the surface and the fluid, okay, temperature difference between the surface and the fluid, okay. So Q by A, it is also called as a heat flux. Q by A is also called as a heat flux. Heat transfer rate per unit area is also called as a heat flux. So Q by A is directly proportional to T suffix S minus T suffix F, okay, where T suffix S is the surface temperature of a plate and T suffix F is the fluid temperature which is flowing over that particular plate, okay. Next we have discussed that we have to normalize this proportionality sign, okay, we have to normalize this particular proportionality sign. So for that purpose we have to introduce one constant of proportionality, okay, constant of or proportionality constant, okay. So for that purpose, here in this equation we have introduced the constant of proportionality and we have transferred this area capital A on this side, so that the equation, we will get the equation in the form of a heat transfer rate, okay, we will get the equation in the form of a heat transfer rate. So heat transfer rate by convection, okay, heat transfer rate by convection is equal to H multiplied by A multiplied by T suffix S minus T suffix F, okay, H multiplied by A multiplied by into bracket T suffix S minus T suffix F, okay, where this H is constant of proportionality called as a convective heat transfer coefficient, called as a convective heat transfer coefficient. Remember this thing. Okay. So where we have discussed that Q is the rate of convective heat transfer, and a heat transfer rate or convective heat transfer rate, we can say that. So Q is its unit is watt. Okay. Then A is the area exposed to heat transfer. Is the area exposed to heat transfer, and its unit is meter square. Area we are always taking in a meter square. Okay. Then Ts, T suffix S is the surface temperature. Okay, which will be in a degree Celsius or degree Kelvin. Okay. Then T suffix F is the fluid temperature which is flowing over that particular surface, and its unit is also degree Celsius or degree Kelvin. Okay. Then H is convective. H is convective heat transfer coefficient. H is convective heat transfer coefficient, which is a proportionality constant. Which is a proportionality constant in this Newton's law of cooling. In this Newton's law of cooling, and we have to determine the unit for this particular H. Okay, we have to determine the unit for this particular H. Okay, that is convective heat transfer coefficient. Okay, so for that purpose, once again we have to consider this Newton's law of cooling equation. Q is equal to HA delta T, or HA multiplied by Ts minus Tf. Okay, so by considering the same equation, we are going to rearrange this equation in the form of a H. Okay, in the form of a H. Okay, in the form of a H, so that on this side, whatever A and Ts minus Tf, these two parameters we are transferring on another side, or right hand side parameter, that is A multiplied by Ts minus Tf, we are transferring on left hand side. So we'll get the equation. We'll get the equation H is equal to Q divided by A multiplied by Ts minus Tf. Okay, H is equal to Q divided by A multiplied by Ts minus Tf. Okay, after transforming the parameters from this side to this side, so we will get the equation H is equal to Q divided by A multiplied by Ts minus Tf. Now unit of Q is watt. Okay, unit of Q is watt. Unit of A is meter square, and Ts minus Tf, that is, it is a change in temperature, so its unit is degree Celsius or a degree Kelvin. So the combined unit of a H we can write as watt per meter square degree Celsius. Okay, watt per meter square degree Celsius. Okay, or if you take this temperature in a degree Kelvin, then also no problem, because you are adding 273 degrees Celsius in a Ts temperature also, and you are adding the 273 degrees Celsius 273 in a TF temperature to convert a degree Celsius temperature into a degree Kelvin temperature, and we are taking the difference. So there will not be any difference in a value of a degree Kelvin and a degree Celsius, because we are taking the difference of these two values. Okay, so for that reason you can take any of the unit for the H, that is watt per meter square degree Celsius or watt per meter square degree Kelvin. Okay, any of the unit is suitable for this particular H, that is convective heat transfer coefficient. That is convective heat transfer coefficient. Getting everyone how we are determining the units of H and K in a conduction? Also in a similar fashion, we have determined the unit for the thermal conductivity. So in remember the difference between thermal conductivity unit and the heat transfer coefficient unit, or convective heat transfer coefficient unit. Okay, so the thermal conductivity unit is watt per meter degree Celsius or watt per meter degree Kelvin. Okay, whereas the unit of H, that is convective heat transfer coefficient, is watt per meter square degree Celsius. Watt per meter square degree Celsius. This is also one type of a MCQ. Okay, this is also one type of a MCQ. So unit of H, or unit of convective heat transfer coefficient, unit of thermal conductivity. Four options will be provided in, and you have to determine the correct option out of that. Okay, so remember this unit. The the convective heat transfer coefficient unit is watt per meter square degree Kelvin or watt per meter square degree Celsius. Okay. Then we have to define this particular convective heat transfer coefficient. So for the definition purpose, we are using the same funda whatever we have used for thermal conductivity. So in thermal conductivity also we have determined or we have defined the thermal conductivity. We have defined the thermal conductivity by considering the surface area which is perpendicular to heat transfer as a unit surface area, and the temperature gradient as a unit temperature gradient, or the temperature difference between the two surfaces is a unit temperature difference, and the thickness of the wall or the or that particular slab is a unit thickness. So at that time, whatever the heat transfer happen, that heat transfer is equal to the thermal conductivity of a material. So that we have discussed for the, or that we have defined for the thermal conductivity. Okay. In a similar fashion also, here in the convective heat transfer coefficient, we are going to define this H. Okay. So H is nothing but what? Convective heat transfer coefficient. Okay. H is nothing but what? The convective heat transfer coefficient, and it is also called as a film heat transfer coefficient, and it is also called as a film heat transfer coefficient. Okay. Remember another one terminology for the convective heat transfer coefficient. Okay. Another terminology for the convective heat transfer coefficient is film heat transfer coefficient, and is defined as the amount of heat transmitted for a unit temperature difference between the fluid and a surface and unit area of a surface in unit time. Okay. So H, what is the meaning of this definition? It means that H is equal to Q when A is equal to 1 and Ts minus Tf is equal to 1. Okay. In a simple language, we can say that when H is equal to Q, when A is equal to 1 and Ts minus Tf is equal to 1. And this particular heat transfer will be happen in a unit time, because the time is more important. So this heat transfer is happening in a unit time. Okay. So whatever the heat transfer happening when A is equal to 1, Ts minus Tf in a unit time, that heat transfer will be considered as a convective heat transfer coefficient. That heat transfer will be considered as a convective heat transfer coefficient. So we can define this convective heat transfer coefficient as the amount of heat transmitted for unit temperature difference between the fluid and surface, and unit area available for the heat transfer, unit area of a surface in unit time. Okay. Unit area of a surface in unit time. Okay. Getting everyone? Now the important factor, remember one thing, the thermal conductivity. Okay. In conduction, the thermal conductivity is the property of a material. Okay. It differ by material. Okay. As material changes, that particular property of a material also goes on changing. That is, for metal, the thermal conductivity is different. For non-metal, it is different. For good insulator, it is different. For liquid, it is different. Liquid to liquid, it is differ. But in this case, the value of H, that is the heat transfer coefficient, value of heat transfer coefficient is depend on a many factors. And it is not a property of a substance. Okay. It depends on a many factor and it is not a property of a substance. Okay. So in which factor it is depend, we are going to discuss that particular factor. Okay. So because it is a fluid property. Okay. We can say that it depends on a fluid motion and it is depend on a fluid properties. Okay. H is depend on a fluid properties and the geometric properties also. So for that purpose, H value is depends on a many factors of a fluid, and it depends on a geometric factor of a that particular material or the substance which is exposed for the heat transfer. Remember this particular point. H is not a property of a substance? It depends on a fluid properties. It depends on a fluid properties. As the fluid properties goes on varying, this H value is also goes on varying. Okay, this value also goes on varying. We have discussed the natural convection and forced convection. So in natural convection, it is the heat is transferred naturally because of a density difference. So in case of a natural convection, the convective heat transfer coefficient value is lesser as compared to the forced convection, because in a forced convection we are flowing air or blowing air over the surface forcefully. Okay, so what is differ between these two particular natural convection and forced convection? So we are changing the fluid properties. Okay, one is nothing but the velocity. Okay, so in natural convection there is very less velocity for the fluid, which is happen because of a density difference. Okay, because of a density difference. Whereas in forced convection, we are changing the velocity. We are increasing the velocity, which is velocity of a fluid which is flowing over the surface. So that in case of forced convection, heat transfer coefficient value will be more as compared to the natural convection. So simple thing. In such a manner, if you take the example of a natural convection and forced convection, so H value is not constant and heat transfer rate is not constant for both the cases. So it depends on a thermodynamic thermodynamic and transport properties of a fluid. So thermodynamic properties means what? Thermal conductivity of that particular fluid, then density of that fluid, then specific heat capacity, then kinematic viscosity of a fluid, then dynamic viscosity, and transport property is nothing but velocity, acceleration of that particular fluid. That is the transport property. So this is the one case on which the heat transfer coefficient or the convective heat transfer coefficient is depend. Whereas in the another case, it also depends on a fluid flow condition. Okay, fluid flow condition. Whereas the fluid flow is a laminar one, or it is a transition one, or it is a turbulent one. Okay, so in case of a laminar flow, that is nothing but the fluid layers are parallel to each other, flowing parallel to each other. So in transition, we can say that it varies according to the Reynolds number. That is the most important thing. We are segregating the laminar, transition, and turbulent flow on the basis of a Reynolds number. So in turbulent case, what happens? The fluid particles are moving so much random. Okay, so much random. That is nothing but turbulent flow. Okay, and in between this laminar and turbulent, there is a transition type of a flow. We can say that the less parallel or less turbulent flow, like that we can consider as a transition region, whereas the Reynolds number of transition flow is greater than laminar flow and less than the turbulent flow. Okay, so we will further categorize this also. Then it also depends on a geometry of a system, which now here geometry, how it is depend on a geometry, because the area is important in Newton's law of cooling. We discussed that area. Now, which surface is exposed to heat transfer, for convection heat transfer? Which surface is exposed? So that surface geometry is also affect on the heat transfer coefficient. That surface geometry is also affect on a heat transfer coefficient. So H is also affected by area of the surface. H is also affected by the area of the surface. So here also we are considering that geometry of the system, the H value or the convective heat transfer coefficient value is depend on the geometry of the system. So there are different kinds of geometries, that is plane wall, cylinder, sphere. Okay, so these are the geometries, simple geometries. There are complicated geometries also. So in that case, we have to determine which surface area is exposed for the heat transfer coefficient, is exposed for the heat transfer. Okay, on that basis we have to determine the heat transfer coefficient. Okay, then the last one is nothing but a thermal condition. Thermal condition means what? The temperature difference or the temperature of the fluid and the temperature of the surface, on which also this particular H value depends, or the convective heat transfer coefficient value depends. Now further thing, we have to find out the electrical analogy for the Newton's law. As we have discussed for the conduction, the electrical analogy for the Fourier's law of heat conduction. In the same manner, here also we need to determine the electrical analogy for the Newton's law of cooling and for the convective heat transfer. Okay, this law is related to the convective, or this law is governing the convective heat transfer. So for that purpose, we can say that the electrical analogy for the convective heat transfer. Okay, so in previous electrical analogy for the conduction, we have discussed about the Ohm's law. Okay, I don't want to go for that particular Ohm's law. In electrical circuit, current is flowing. Okay, and it is flowing due to the potential difference. Okay, that is nothing but dV, and this flow of current is resisted by the resistance offered by that particular circuit, or the oppose will be done by that by the resistance for the flow of a electric current. Okay, so I is nothing but what? The electric current flowing through the circuit. dV is the potential difference, and R is the resistance offered for the flow of electric current. Okay, so that is the Newton's law. I is equal to dV divided by R. Now our Newton's law of cooling, what it stated, the rate of convective heat transfer per unit area is directly proportional to the difference between surface temperature and the fluid temperature. So it is the statement of a Newton's law of cooling. So on that basis, after normalizing, we will get this equation, that is Q is equal to H multiplied by A multiplied by Ts minus Tf. Okay, so we have discussed this equation, Q is equal to H multiplied by A multiplied by Ts minus Tf. Now we have to determine, we know that current is analogous. In the last lecture also only we have discussed this electrical analogy for the conduction. We determined that the I is analogous to Q. Okay, the flow of electric current is analogous to the flow of heat. Okay, so that is I is analogous to Q. Then the potential difference dV. Okay, that is the voltage difference. We can say that the potential difference dV is analogous to the temperature difference. Okay, is analogous to the temperature difference. So in case of Ohm's law, the current is flowing because of a potential difference. In case of heat transfer, the heat is flowing due to the temperature difference. That in this particular case, for the Newton's law, temperature difference is nothing but Ts minus Tf. So dV is analogous to Ts minus Tf. Now remaining part is nothing but H multiplied by A. Now in case of electrical analogy, resistance at the denominator side. Okay, at the denominator side. So whatever remaining than the Ts minus Tf, whatever remaining part, that is H multiplied by A, we need to transfer this particular parameter on the denominator side without changing the significance of law, without changing the significance of Newton's law of cooling, or without changing the significance of this particular equation, without changing the significance of this particular equation. So we are rearranging this equation in the form of a Ohm's law. Okay, so we have rearranged this. So we have transfer H multiplied by A to the denominator side. Okay, denominator side. So we will get the equation Q is equal to Ts minus Tf whole divided by 1 divided by H multiplied by A. Okay, 1 divided by H multiplied by A. So after doing this, the significance of this equation will not change. Okay, 1 divided by H multiplied by A. Now if you compare this equation, I is equal to dV divided by R, and this equation Q is equal to Ts minus Tf whole divided by 1 divided by H multiplied by A. So we have discussed that I is analogous to Q, dV is analogous to Ts minus Tf, and remaining part, denominator part, is the resistance. So in a similar fashion, the denominator part is nothing but 1 divided by H multiplied by A. 1 divided by H multiplied by A. Now this particular part will be called as a convective thermal resistance for the heat flow. This 1 divided by H multiplied by is called as a 1 divided by H multiplied by A is called as a convective thermal resistance for the convective heat transfer. Thermal resistance for the convective heat transfer. So instead of this 1 upon HA, we can write Q is equal to Ts minus Tf whole divided by RTH in bracket RTH convection, suffix convection. That is the convective thermal resistance. We can say convective thermal resistance. Getting everyone? Is there any question? Now where RTH convection, that is the thermal resistance for the convective heat transfer, is equal to 1 upon HA. 1 upon HA, where this H is nothing but convective heat transfer coefficient, H is nothing but convective heat transfer coefficient, and A is nothing but area exposed for the heat transfer. A is nothing but area exposed for the heat transfer. Getting everyone? Getting everyone? Now after doing this, we can easily draw the equivalent electric circuit for the Newton's law of cooling. Equivalent electric circuit for the Newton's law of cooling. What? So heat is transforming. Okay. Why it is transforming? Because of a temperature difference. Which temperature difference? The surface temperature and a fluid temperature. So surface temperature is greater than the fluid temperature. So from surface to fluid, the heat is transforming. So two temperatures we have shown over here. One is Ts and another one is Tf. Okay. And the heat is transforming from the surface to the fluid. So heat transformation direction we have provided Q, and this Q is provided over here. And the resistance offered for this particular heat transfer, that is nothing but it is provided by this particular resistance symbol, and its value is or its equation for the resistance is 1 divided by H multiply A. 1 divided by H multiply by A. So here 1 divided by H multiply by A called as a convective thermal resistance to heat flow. 1 divided by H multiply by A is called as a convective thermal resistance to heat flow. Convective thermal resistance to heat flow. Getting everyone? What is mean by thermal resistance for the heat flow? How we have determined that, and how we have analogous the electric circuit with the Newton's law of cooling, and the different factors on which the convective heat transfer coefficient is depend. Is there any question, any doubt? Okay, so write down where we reach. I think here we have to determine the H. Okay, the unit of H. Okay, so write down next. Write down next. H is equal to, rearrange equation. We can say that rearrange the equation of a Newton's law of cooling in the form of a H. In the form of a H. Okay. So H is equal to Q divided by H is equal to Q divided by A multiply by Ts minus Tf. Q divided by H multiply by Q divided by A multiply by Ts minus Tf. So its unit will be H is equal to, or its unit will be watt per meter square degree Celsius, watt per meter square degree Celsius, or watt per meter square Kelvin. Watt per meter square degree Celsius or watt per meter square Kelvin. Okay. Then next, convective heat transfer coefficient. Okay. Definition of convective heat transfer coefficient. Definition of convective heat transfer coefficient. In bracket small h. Write down the definition. Write down the definition. Coefficient of convective heat transfer. Coefficient of convective heat transfer. The coefficient of convective heat transfer. The coefficient of convective heat transfer. H. H. Also known as. Also known as. Also known as. Also known as film heat transfer coefficient. 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 Film heat transfer coefficient. Defined as. Defined as. Defined as. Defined as. Defined as. Defined as. Defined as the amount of the amount of heat transmitted, the amount of heat transmitted, the amount of heat transmitted, the amount of heat transmitted for a unit temperature difference 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 between the fluid between the fluid between the fluid and surface 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 and unit area of a surface and unit area of a surface and unit area of a surface in unit time and unit area of a surface in unit time. Okay, unit area of a surface in unit time. Then next, write down the value of H, the value of H, that is convective heat transfer coefficient. The value of H, the value of H, the value of H, the value of H depends on the following factors. The value of H depends on the following factors. The value of H depends on the following factor. Which are that factor? Depends on a following factor. The first one is thermodynamic and transport properties. Thermodynamic and transport properties. Thermodynamic and transport properties, that is thermal conductivity, comma, density, comma, specific heat capacity, then kinematic viscosity, then dynamic viscosity, then velocity. Okay, so these are the thermodynamic and transport properties of a fluid. Okay, these are the thermodynamic and transport properties of a fluid. Okay, so second factor is fluid flow conditions. Fluid flow condition. fluid flow conditions. Fluid flow condition. Okay. So that is nothing but whether the flow is laminar one, whether the flow is transition one, and whether the flow is turbulent one. Okay. So on that also the H value depend. So fluid flow condition, that is laminar, transition, and turbulent. Fluid flow condition, that is fluid flow conditions, that is laminar, transition, turbulent. Then third one, geometry of the system. Third one, geometry of the system. That is whether the geometry which is heat transferring, that geometry is plane wall or a cylinder or a sphere. So on that also heat transfer coefficient value depend. Geometry of the system, that is plane wall, cylinder, sphere, etc. And the last one is thermal conditions. Last one is thermal conditions. Thermal conditions means what? The temperature of a surface, temperature of a fluid, and the difference between these two temperatures. So that is temperature. Thermal condition means temperature. Thermal condition means temperature. Okay. Is there any doubt, any question? Okay. Next. Electrical analogy for Newton's law. Okay. Electrical analogy. You next heading, electrical analogy for Newton's law. Electrical analogy for Newton's law. Okay. So Ohm's law, write down the Ohm's law. I is equal to dV divided by R. 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 According to Ohm's law, I is equal to dV divided by R. Newton's law of cooling. Next, Newton's law of cooling. So you can give this as equation number 1. And the Newton's law of cooling, Q is equal to H multiplied by A multiplied by Ts minus Tf. Q is equal to H multiplied by A multiplied by T suffix S minus T suffix F. Further, we are rearranging this equation to find out the thermal resistance. Okay. So we have rearranged this equation in such a manner that there is no change in a significance of this particular equation. Okay. So Q is equal to T suffix S. Q is equal to T suffix S. Q is equal to T suffix S. Q is equal to T suffix S minus TF whole divided by 1 upon H multiplied by A, whole divided by 1 upon H multiplied by A. So where this particular 1 upon H multiplied by A is called as a thermal resistance for convection heat transfer. Thermal resistance for convection heat transfer. So we can write Q is equal to, Ts minus Tf whole divided by in bracket RTH suffix convection, in bracket RTH, that is thermal resistance for convection heat transfer. RTH convection. Okay, RTH convection. So where what will be the equation for RTH convection? So RTH convection, that is the thermal resistance offered for convective heat transfer, will be equal to 1 upon H multiplied by A. 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 Then further, if you want to draw the equivalent electric circuit for the convection heat transfer, for the Newton's law of cooling, then we can draw in this particular fashion. Okay. So temperature difference, Ts, Tf. Okay. So surface temperature is Ts, fluid temperature is Tf, and heat is transferring from surface to the fluid. So heat transfer direction shown over here, and Q amount of heat transferring, and the resistance offered to heat transfer is nothing but 1 upon H multiplied by A. So resistance symbol, and this particular resistance is a thermal resistance offered for convection heat transfer. Okay, and its value, its equation is 1 upon HA. Okay, its equation is 1 upon HA. 1 upon H multiplied by A. Okay, getting everyone? Any doubt, any question? Here 1 upon HA called as a convective thermal resistance, 1 upon H multiplied by A, 1 upon H multiplied by A called convective thermal resistance, to heat flow. Convective thermal resistance to heat flow. Understood? Everyone, please comment in the chat box. If you have any doubt, then you can also ask, or you can mention your question in the chat box. Okay, so these are the basic concepts of heat transfer. Okay, if you clear this, then only you will understood further things about this particular convection chapter. Okay, so we will discuss the convection in detail in chapter number 4, I think, in chapter number 4. So at that time we have to recall these particular basics also. Then the problem number 1, write down the problem number 1 so that it will be clear how to apply the Newton's law of cooling. Problem number 1. Problem number 1, write down: the hot plate 1 meter by 1.5 meter, the hot plate 1 meter by 1.5 meter is maintained at 300 degrees Celsius. Is maintained at 300 degrees Celsius. Full stop. Is maintained at 300 degrees Celsius. Full stop. Air at 20 degrees Celsius. Air at 20 degrees Celsius. Air at 20 degrees Celsius. Air at 20 degrees Celsius blows over the plate. Air at 20 degrees Celsius blows over the plate. Air at 20 degrees Celsius blows over the plate. Full stop. If the convective heat transfer coefficient is is 20 watt per meter square degree Celsius. If the convective heat transfer coefficient is 20 watt per meter square degree Celsius. Calculate the rate of heat transfer. 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 Okay. Have you noted? Now further, we have to note down the given data. Find out the given data. What is provided in the problem? First is nothing but area of the plate is provided. Okay. 1 meter by 1.5 meter. Okay. Area is provided. Hot plate area is provided as 1 meter by 1.5 meter. Then further, the plate temperature is provided. That is nothing but the surface temperature is provided 300 degrees Celsius. Then further, the air temperature or the fluid temperature which is flowing over that particular plate is provided. Air at 20 degrees Celsius. That is nothing but TF is provided. If the convective heat transfer coefficient is 20 watt per meter square degree Celsius, H is provided. Okay, H is provided. H value is provided and it is 20 watt per meter square degree Celsius. And we have to determine the Q. That is nothing but rate of heat transfer by convection we have to determine. Okay. Now note down the given data as A is equal to that is the area of or the surface area of the plate, area 1 meter by 1.5 meter, which will be equal to 1.5 meter square. 1 into 1.5 meter, that will be equal to 1.5 meter square. Then next, surface temperature is provided. Okay, surface temperature of a plate is provided. That is T suffix S. T suffix S is provided. And it is equal to 300 degrees Celsius. It is equal to 300 degrees Celsius. And then further, the fluid temperature, that is the air temperature which is blowing over the plate, it is provided as T suffix F is equal to 20 degrees Celsius. T suffix F is equal to 20 degrees Celsius. And the last T is nothing but what? H is provided. No? H is provided. H is equal to how much? 20 watt per meter square degree Celsius. H is provided. H is equal to 20 watt per meter square degree Celsius. And we have to determine the rate of heat transfer by convection. That is Q we have to determine. Q we have to determine. Okay. Then we know the Newton's law of cooling for the convection. Okay. We know the Newton's law of cooling for the convection. That is Q is equal to H multiplied by A multiplied by into bracket TS minus TF. H multiplied by A multiplied by into bracket TS minus TF. Okay. So just put up the values of a given data and find out the Q. Okay. Put up the values of H, A, TS and TF in this particular equation. You will get the Q value. So Q is equal to H value is 20 watt per meter square degree Celsius. 20 multiplied by area is 1.5 meter square. 1.5 multiplied by TS is 300. So TS is 300 and TF is 20. TF is 20. Just put up the values of parameters from the given data and determine the Q. Determine the Q. That is the rate of heat transfer by convection. Determine Q. Okay, can you mention your answer in the chat box? Can you mention your answers in the chat box? 8400. Okay, great. So unit will be watt. Unit will be watt. Okay. So Q is equal to 8400 watt. Okay. 8400 watt. This is the answer for the first problem. Getting everyone? Understood how to solve the simple problems. Okay. This is the simple problem that if you remember the formula, then you can put up the values and find out the answer. Okay. So this type of problems also 76 roll number. 76 roll number. Is there any doubt? Okay. So then next problem, note down the statement of next problem. Statement of next problem. Problem number two. Problem number two. A wire. Problem number two. A wire 1.5 mm in diameter. A wire 1.5 mm in diameter. 1.5 mm in diameter. A wire 1.5 mm in diameter and 150 mm long and 150 mm long and 150 mm long and 150 mm long 150 mm long is submerged is submerged is submerged is submerged in water a wire 1.5 mm in diameter 1.5 mm in diameter and 150 mm long and 150 mm long is submerged in in water at at atmospheric pressure at atmospheric pressure at atmospheric pressure full stop an electric current an electric current an electric current is passed through wire. An electric current is passed through wire. An electric current is passed through wire and is increased and is increased and is increased and is increased until the water boils and is increased until the water boils at 100 degrees Celsius until the water boils at 100 degrees Celsius until the water boils at 100 degrees Celsius full stop degrees Celsius full stop under the condition if convective heat transfer coefficient under the condition if convective heat transfer coefficient is 4500 convective heat transfer coefficient is 4500 watt per meter square degree Celsius convective heat transfer coefficient is 4500 watt per meter square degree Celsius. Watt per meter square degree Celsius. Full stop. Find how much electric power. Find how much electric power. Find how much electric power must be supplied. Find how much electric power must be supplied to the wire, to the wire, to the wire to maintain the wire at 120 degrees Celsius. To maintain the wire, at 120 degrees Celsius. Okay, to maintain the wire at 120 degrees Celsius. Okay, getting the problem statement, everyone. So wire is provided. Now here there is no rectangular geometry. Here cylindrical geometry is there. Wire is a cylindrical geometry. Okay, because it is having diameter and it is having the length. So wire is a cylindrical geometry. Okay, so and in this particular case the wire diameter is provided and the cylinder the wire length is provided. Okay, so on that basis we can determine the surface area available for the heat transfer from wire to water. Okay, we can easily determine the surface area available for heat transfer from wire to water. Now water is boiling. Okay, water is boiling. Okay, because the heat is transferring from wire to water. Okay, because of that the water is boiling at 100 degrees Celsius. Now here the fluid temperature we have to consider as 100 degrees Celsius. Why it is boiling? Because the electric current is transferring through that particular wire, and due to that the heat is produced by the wire. Heat is produced by the wire and that heat is transferred to the water, and due to that water is boiling. Okay, now in the present situation water is boiling at 100 degrees Celsius. So we have to consider the fluid temperature as 100 degrees Celsius. We have to consider the fluid temperature as 100 degrees Celsius. Under the condition, at this particular condition, if the convective heat transfer coefficient is 4500, okay, under this particular condition the convective heat transfer coefficient is 4500 is provided. Okay, means what? The heat is transforming from wire to water and water is boiling, and at that particular condition the convective heat transfer coefficient is 4500 watt per meter square degree Celsius. Now to maintain this particular situation, electric power is consumed. Okay, that particular wire consume the electric current. Okay, or the power will be supplied to that particular wire so that the electrical current will be converted into a or electrical energy will be converted into a heat energy. Okay, electrical energy will be converted into a heat energy. So power will be consumed, electric power will be consumed. Now condition is that we have to maintain the temperature of wire at 120 degrees Celsius. Okay, we have to maintain at any cost. Okay, at this particular condition 100 degrees Celsius, at 100 degrees Celsius water is boiling and wire temperature is 120 degrees Celsius. Now to maintain wire temperature 120 degrees Celsius, how much electrical power should be supplied to that particular wire? That is our main question, or the finding through this particular problem. Okay, we have to find out the power consumption. Okay, so if you recall this the unit of a power, it will be very simple problem. If you recall the unit of a power at this particular condition, if you recall the unit of a power, the problem statement is a simple one for you. What is the unit of power? Power's unit काय असतं? Can you mention in the chat box, or you can unmute and you can tell me what is the unit of a power?
Watt.
Watt. Okay, great. So watt is the unit of a power. And what is the unit of our heat transfer rate? What is the unit of a heat transfer rate? It is also watt. Here only we have mentioned. So Q is equal to 8400 watt. So unit of a Q is, that is the rate of heat transfer, is watt. Now we can say that the electric power, how in a assumption condition, we can say that the electric power which must be supplied to the wire will be equal to the total convective heat loss from wire to water. Okay, can you say that? Okay, under the assumption that there is no heat loss to the surrounding, we can say that how much power we have supplied to the wire, that much power or that much heat is released by that particular wire to the water. Okay, that much heat is released by that particular wire to the water. Getting everyone? Okay, getting everyone? समजतंय? वॉटर जे काही हीट ट्रान्सफर रेटचं युनिट आहे वॅट आहे, पॉवरचं युनिट काय असतं, वॅट असतं. ओके, सो अंडर दिस सर्कमस्टन्सेस वी कॅन से दॅट how much heat is supplied to the wire, that how much electric energy is supplied to wire, that much energy is converted into a heat energy. That much energy is converted into a heat energy. So to determine the electric power, we need to determine the convective heat transfer rate from wire to water, from wire to water at this particular condition. Condition काय आहे? कंडिशन आहे आपल्याकडे की वॉटरचं टेम्परेचर आहे 100 डिग्री सेल्सिअस अँड वायरचं टेम्परेचर आहे 120 डिग्री सेल्सिअस. ऍट दिस कंडिशन द हीट ट्रान्सफर कोएफिशियंट इज 4500 watt per meter square degree Celsius. Okay, and at this condition we have to determine the electric power, and to determine the electric power we need to determine the heat transfer from wire to water. Heat transfer from wire to water. Getting logic? Now wire is a cylindrical geometry. Okay, first thing is very important, we have to decide the geometry. Wire, imagine the wire having the diameter and wire having the length, so it is a cylindrical geometry. Okay, so in that case we have to determine the area of that particular cylindrical geometry. So area will be D is equal to 1.5. Okay, diameter is provided 1.5 mm and length is provided as 150 mm. Okay, so the surface area of the cylinder, the equation for surface area for the cylinder is A is equal to pi dl. A is equal to pi dl, where the D is the diameter of that particular cylindrical geometry and L is the length of that particular cylindrical geometry. In this case our geometry is the wire, so the diameter of wire and the length of a wire. So pi is equal to, okay, area is equal to pi multiplied by 1.5 into 10 raised to minus 3 10 raised to minus 3. It will be converted into a meter, multiply by length, how much? 0.15, right? 0.15. 1.5 multiplied by 10 raised to minus 3 multiplied by 0.15, because length is 150 mm, we can convert it into a 0.15 meter. Okay, so meter मध्ये कन्वर्जन केलेलं आहे ह्याचं. Okay, so calculate area now. What will be area? Calculate area. Here also, then further you calculate the area, then further what is given data? T suffix s. T suffix yes. It is provided as how much? Surface temperature of a wire. Okay, it is 120 degrees Celsius. 120 degrees Celsius. Okay, and then further T suffix f. T suffix f is provided. T suffix f is provided. Okay, and what? How much it is? That is water temperature. Water is boiling. Okay, boiling at a 100 degrees Celsius. Boiling at a 100 degrees Celsius. So water temperature will be 100 degrees Celsius. Fluid temperature will be 100 degrees Celsius. So it is provided. Then further, we have to determine the power supplied to wire. So for that case, we can say that electric power which must be supplied is equal to total convection heat loss. Convection heat loss. Okay, so we can say that this, so convection heat loss from wire to water. Convection heat loss from wire to water. So electric power which must be supplied is equal to total convection heat loss. Total convection heat loss. कुणाकडनं heat loss होणार आहे? वायर कडून heat loss होणार आहे कुणाला? तर वॉटरला. So we have to determine that particular heat loss so that we can easily say that whatever the heat loss happen from the wire to the water, it is equal to the electric power supplied to the wire. Electric power supplied to the wire. So apply our Newton's law of cooling. Apply our Newton's law of cooling. Simple. What is our Newton's law of cooling? Q is equal to H multiply by A multiply by in bracket Ts minus Tf. That is our Newton's law of cooling. Okay. So consider here the Newton's law of cooling. Q multiply by H multiply by Ts minus Tf. Okay. Just put up the values and find out the answer. Just put up the values and find out the answer. Values H is how much? 4,500. Okay, H is 4,500. Multiply by area. Area. Have you calculated this area? What is the value of area? Can you comment in the chat box? Area value 7.068 into 10 raised to minus 3, right? Everyone? Have you calculated, everyone? Area? Okay, so 7.068 multiply by 10 raised to minus 3. Shall I put up this value? 10 raised to minus 3 is the area. Okay, and it is in a meter square. It is in a meter square, right? So area we determine. So just put up that area over here. 7.068 multiply by multiply by 10 to the power minus 3. Okay, 10 to the power minus 3 multiply by in bracket TS value is 120 and TF value is 100. Okay, so tell me Q now. Calculate this and tell me Q value. $636. Please check that this is 7.068 multiplied by 10 raised to -3 or -4.
Sir, -4, sir.
Right now, -4. It is -4. So it will be less. This is area, I think, somewhat calculation.
3.61.
Okay. So now, so Q becomes, Q is equal to
63.61.
63.61. Q is equal to 63.61. Okay. And its unit will be watt, and which will be equal to power supplied to the wire, right? Power supplied to the wire. Which will be equal to the power supplied to the wire. Getting everyone? Is there any doubt, any problem in this particular answer? Whether you understood everyone how to solve the problem on a convection. So just put up your roll numbers. I think 10-15 minutes I have taken extra. You can put up your roll numbers in the chat box. If you have any doubt, you can ask. Otherwise, you just put up your roll numbers in the chat box and we'll stop here.